All right. So again, this the leading theory that it's a black hole that is causing this at the center of these galaxies, and so in fact quasars turn out to be galaxies, where you're only seeing they're so far away that you can only see the center of the active part. The other stars are just so far away that they're too dim for us to see. Anyhow, remember it's the accretion disk, right? The accretion disk is because you have so much gravitation. Remember we're talking about billions and billions of times the mass of the sun that makes up this supermassive black hole. That this material is as it rotates around, it's rubbing against itself. It's just friction, and then that friction is turned into electromagnetic energy the friction, of course, is getting all the electrons and protons to be freed from their individual atoms, and so those electrons and protons circulate around the magnetic field lines, and that's in fact what we call synchrotron radiation. It's a very famous. It doesn't look like a star. It doesn't look like the radiation from a star, and so we can. And sometimes it's also called non-thermal radiation. So the fact that there's charged particles that are oscillating around these magnetic field lines, which again we have a name for that. It's called synchrotron radiation. We can detect that whether it's synchrotron radiation or whether it's thermal radiation from starlight, and these active galaxies at their center it's synchrotron radiation. It's not stellar light. It's not non-stellar light is another name for it. All right. So so that's the supermassive black hole. So this is the thing about anywhere from 10 to 20% of the mass of the accretion disk is radiated back out into space, and of course before it goes over the event horizon, and then just becomes part of the supermassive black hole. So some of these black holes are taking in something like the mass of the sun per year. Some of them about 10 times the mass of the sun per year. Some of them, maybe one solar mass per 100 years or something like that. So that's basically the difference in in what we would call the activity, right? How much energy, how much non-thermal energy is coming from these. And of course, here's a nice picture. Let me just talk about. Let me focus on M87. So this is a very well-known active galaxy. It's one of the nearest. I think it is actually the nearest active galaxy to the Milky Way. Notice there's we're seeing in the accretion disk material that is red shifted, so it's moving away from us. Then there's material that's blue shifted that seems to be moving towards us. This is some of that jet of material that we saw in the first picture. The other thing that's really special about this, and hopefully this is during a time when you're actually attending class, but I'll have the video on there. There's actually a telescope. It's actually not one telescope. It's multiple radio telescopes that were put together across the entire Earth, and were synchronized, right? So it's really, the timing of them was really important, and those all those radio telescopes, they were called the Event Horizon Telescope, in fact, and it was specifically to look at these supermassive black holes and try to get an image. And in fact, with M87, which is the very first one that we looked at, we actually got a result just a few years ago, as a matter of fact. And that's I posted that video on Blackboard, so you can see that this was an incredible success. We made this proposal, that we will be able to use using basically a radio baseline the size of the Earth, with all these different radio telescopes. You can't build a radio telescope the size of the Earth, but you can have individual ones scattered all over the Earth and then aim them at the same object, and that basically acts like a giant telescope. Well, it's a radio telescope in this case, and it allowed us to actually map the and for the very first time take a picture, if you will, in radio, of course, of the supermassive black hole at the center of M87. So that was a wonderful success. So this is one might expect the radiation to be mostly X-rays and gamma rays, but so here's what happens with this is, coming right off of the disk, the accretion disk, I should say, there tends to be like a name for this would be like these donut-shaped. This is just basically matter that's falling onto this accretion disk, but it forms like a donut shape around it, and so the X-rays and gamma rays, which are created right at the accretion disk, get absorbed in this donut-like material. I mean, it's just like star material basically, with hydrogen and helium and maybe some other stuff. And so when that happens, that gets the X-rays and gamma rays get absorbed and then re-emitted, and then sometimes that's called being reprocessed. And so you get them into, instead of being in the X-rays and gamma rays, they get into much longer wavelengths. So you get stuff in the ultraviolet, in the visible, and even in the infrared, and especially in the infrared. So this is what I mentioned before about synchrotron radiation. So you have charged particles that get trapped in these magnetic field lines, and they spiral around, and they emit synchrotron radiation. And in fact, it looks quite different than thermal radiation. We can easily distinguish between those. All right, so that is the summary of the chapter. Remember this, so let me go over this since I got a little bit of time left here. So you got Hubble's classification scheme, the basic three types of galaxies: spiral, elliptical, and irregular. Okay, but of course we've subdivided some of them. The spiral galaxies, there are barred spirals and just regular spirals, and then of course there's the SA, B, and C, or SBA, SBC, SBB, and it's capital S, capital B, right, for barred spiral, and the A through B is the size of the nuclear bulge and the how tightly the spiral arms are wound. So those the extreme would be, and the A is the largest nuclear bulge, and then C would be the smallest, and then A would also have the most tightly wound spiral arms, and then C would have the loosest. With ellipticals, they go from E0, which is the most spherical, and all the way to E7, which is the most elliptical, basically like football shaped. Remember, there's also what's called the lenticular galaxy, the S0, which Hubble originally thought was the transition between ellipticals and spirals, which does not seem to be the case. In fact, we'll talk about how we think elliptical galaxies come into being in the next chapter. That's really what a big part of the next chapter is devoted to. Remember, elliptical galaxies have almost no gas and dust, really old, old type 2 stars, which have really low metal content. Spiral galaxies still have a good deal of, up to maybe 20% of their mass still in the form of gas and dust, so new star formation is still taking place in spirals. Irregulars, in fact, don't have an overall shape, and they tend to be smaller, although ellipticals can be pretty small too. You can have what they call dwarf ellipticals, and then you can have supergiant ellipticals. Irregulars, there's basically two general types. Just normal irregulars, and then irregular type 1, and then there's irregular type 2. The irregular type 2 looks like an exploding galaxy, basically. It looks like there's if you photographed an explosion, that's kind of what those irregular galaxies look like. They have tremendous amounts of gas and dust, and new star formation is taking place all the time. These things have really young, hot blue stars in about half their mass. So 50% of the mass of irregular galaxies is still tied up in gas and dust. Let's see, uniform. So remember, we extended the distance ladder using Cepheid variables, or Lyra. Then we use standard candles, in other words, supernova type 1 were standard candles. And then, of course, we found that there was different things that we could actually use this thing called the Tully-Fisher method for spiral galaxies to determine the distance to spirals, because if they're spinning faster, that means that there's more mass in the spirals mean that they're spinning faster, and so when they're spinning faster, the absorption lines are broader, and so there's a mathematical relationship between how broad how broad the absorption lines are in spiral galaxies, and of course what their absolute luminosity is. And then, of course, the last one, of course, is not related to luminosity at all. It's just the redshifts, right? The Hubble's redshift distance law. There's clusters of galaxy. There's superclusters. I'm not quite ready to get into superclusters yet. That's actually for a later chapter when we talk about the structure of the universe itself. Anyhow, there's clusters of galaxies. They tend to have thousands of galaxies that are gravitationally linked. We are actually in what's called the local group. There's just 3 spiral galaxies: us, Andromeda, the Milky Way, Andromeda, and M33, and then a bunch of maybe 50 or so small little irregular galaxies. All right, so the clusters again contain thousands of galaxies. Hubble's law, we talked about that. Don't forget that just because it seems like the redshift indicates that some of those galaxies really far away are moving faster than light. They're not. Nothing can travel faster than light. So we have a whole table that shows, if you know what the redshift is, even if it's like a 5 or something like that, a redshift of 5, which you'll see what I mean when you look at the table, you can tell how far away it is. You can tell how far away that particular galaxy is. Remember, when we just distinguished between active galaxies, which are producing a lot more energy, there are 3 basic types: Seyfert, radio, and quasars. Quasars were the first ones discovered. Seyfert are always spiral galaxies. Radio galaxies, most of their energies coming in the form of radio waves, as their name implies. And of course, they have these high-speed jets, depending on what angle you see them on. We think that the thing that's causing this is these supermassive black holes at the centers, and of course, the matter that's the matter that in the accretion disk, really, that's turning that heat that's taking place as this accretion disk spins around very, very quickly. That heat gets basically turned into energy, and that's how these things are active, considered active galaxies. All right, so that's it for chapter 24, and let me stop this thing.